Good morning and welcome to today's webinar on solvent extraction. I'm Mauricio Villegas, Business Development Manager here at Koch Modular. And today we'll be discussing an energy efficient and cost-effective solution to remove contaminants from wastewater. Now, as resources become more scarce and we continue to search for more sustainable, efficient, and cost-effective solutions to purify and recycle industrial wastewater, solvent extraction has proven to be an effective process to remove difficult to remove contaminants and even shows promise in removing emerging contaminants such as PFAS from wastewater streams. Our presenters will discuss the theory behind the extraction process design and pilot testing considerations, and share real-world applications. Now, if you have any questions, please use the chat window for any of your questions, and we'll spend a few minutes at the end of the presentation to answer any of those questions. Any questions not answered will be followed up with after the webinar, and a copy of the presentation will be made available about next week. Now, presenting today is Brendan Cross. Brendan is a principal extraction engineer at Koch Modular and brings about 15 years of experience in extraction application. He has a bachelor's degree in chemical engineering from Columbia University. Supporting Brendan is Don Glatz, our manager of extraction technology, and Don brings over 30 years of experience in extraction technology and holds a chemical engineering degree from Rensselaer Polytech Institute and an MBA from Fairleigh Dickinson. Would also like to just acknowledge our pilot plant team. Without their support, a lot of this work would not be possible. Tom Lightfoot is our pilot plant manager. We also have our pilot plant team and Elena, our senior analytical chemist. Just a quick brief about Koch Modular, who we are. We are a joint venture company with Koch Glitch, and we bring over 40 years of experience supporting the chemical processing industry. Before we get started, I just had a quick poll question just to kind of see, what the attendance looks like. So if you can, there's a poll question that has just come up, and that is, how familiar are you with using extraction technology for the removal of wastewater contaminants? So you can just take a minute and answer the question and see what the, what that looks like. We'll give it about 30 seconds. Answers starting to come in. So let's see, just give another minute, another few seconds. And right now it looks like we have somewhere around the middle. So we have kind of a good mix. One person has a lot of experience. We have a couple very, some moderately, some slight, some not at all. So I appreciate everyone taking the time to answer that. And with that, I'll hand it off to Brendan. Thank you.
Thanks, Mauricio. So why would you be interested in choosing solvent extraction when looking at processing an industrial wastewater stream? And really what it comes down to is there's substantial energy savings over traditional processes like distillation. Wastewater contaminants are often higher boiling than water or non-volatile. So if you have a high boiling contaminant, it can be separated by using distillation, but the energy cost is high. And that's also true if you have a non-volatile component. Those can also be removed by distillation or evaporation, but the energy cost is high there as well. And that's essentially because the amount of energy required to boil off all of that water is extremely costly. So solvent extraction is a way to greatly reduce that overall energy cost. And that's because the solvent recovery steps downstream the extraction column require less energy generally than looking at a distillation column or another similar unit operation like evaporation. Some examples of contaminants that we've seen in wastewater and design processes around are things like carboxylic acids, metal ions, or organofluorines. Solvent extraction wastewater processes typically use a solvent that's either going to be more volatile than water or less volatile than water, or just non-volatile entirely. So that difference in volatility or comparative volatility versus the organic solvent yields different recovery processes. And I'm going to be going through 3 case studies today where an optimal overall solvent extraction process was developed through pilot testing. And you'll see those different solvent recovery processes depending on that relative volatility of the solvent versus water show up in each of those case studies. Just one more thing before I move on. Laboratory and pilot plant testing is required to develop and de-risk and design the extraction step. Generally speaking, whenever you have an extraction column, you always want to run a pilot test. So before I get to these case studies today, I'm going to give everyone a little bit of background on solvent extraction and solvent extraction columns. I'll spend a little bit of time on our extraction column technology, and also spend a little bit of time on pilot testing as well. Then I'll dive into the three case studies that I mentioned earlier. So quick overview on solvent extraction. Solvent extraction is where you have some feed stream, like a wastewater stream, that contains some solute or contaminant that you're trying to remove. So this slide shows a single extraction stage. You have that feed, you contact it with an immiscible solvent, allow the two phases to mix together, allow mass transfer to take place. And then after the phases separate and decant, you're left with an extract phase and a raffinate phase. The extract phase essentially is a solvent that has hopefully a large fraction of that solute you're trying to extract, or the contaminant you're trying to extract. And the raffinate is essentially the leftover feed stream that has most of that solute or contaminant removed. When we talk about extraction processes, there's a few terms that we commonly use. First is the fraction unextracted. That's essentially just the amount of solute left in the raffinate versus what came into the extraction step in the feed. For this example, it's 20%. The distribution coefficient that we use very frequently essentially shows you how good of a solvent you have to extract the solute out of the feed. And it's defined as the concentration of solute in the extract divided by the concentration of solute in the raffinate, both on a solute-free basis. For this example, it's fairly high with a distribution coefficient of 8. The extraction factor is something we also often use when evaluating an extraction process. So it's essentially the solvent to feed ratio times the distribution coefficient. For this process, it's high with a value of 4. Typically, we like to target 1.3 at Koch Modular for an extraction process to be economical overall, but that's very process dependent as well, and depends on the value of the product that you're looking to extract and possibly purify, and also just the overall process conditions itself. But generally speaking, we look to target 1.3. Typically, one extraction stage isn't enough to get the amount of solute recovery or contaminant removal that you're looking for. The previous slide, we had 80% removed, but generally speaking, that's probably not enough. Usually we see 95 to 99% removal as the target. So what you can do is something called cross-flow extraction, and that's essentially where you're contacting that feed stream multiple times with fresh solvent, in this example 4 times, to get higher levels of extraction. This is often done in industry through batch washing or batch extraction processes, where a feed stream is contacted with solvent, the phases are allowed to separate, the extract's removed, and then it's contacted with fresh solvent again. This isn't the most economical way to design an extraction process because you're using a lot of solvents, and the cycle time for the overall process can be long because it's typically done batch-wise commercially. So something else you can do is something called countercurrent extraction. This is essentially the mode of operation of extraction columns. So the process here is that you have your solvent flowing countercurrently against the feed. And by taking this type of approach, you can greatly reduce the amount of solvent that's required. And the more you reduce the amount of solvent, the overall economics of the process are going to be much more attractive, because almost always that solvent's going to be recovered downstream through distillation rather than extraction column. So you'll greatly reduce the energy requirements of the overall process and also the capital cost as well. And I'm going to be going through that when I talk about these case studies later in today's presentation. This is what a typical countercurrent extraction column looks like. So this could be a packed column or an agitated column like a Schiebel column. You have your feed entering at one point of the column. Here it's entering at the top, descending the column and leaving as raffinate. And it's the continuous phase in this process shown on this slide. Here the solvent's ascending the column as the dispersed phase. Those droplets flow up the column. They form a controlled liquid-liquid interface at the top, and that solvent leaves as extract. So before I mentioned that the volatility of the solvent relative to water has an implication on how the downstream solvent recovery operations are designed. So if you have a high boiling solvent or a volatile solvent relative to water, a typical extraction process looks like this, where you have an extraction column, you have your aqueous feed coming in on the left, leaving the bottom of the extraction column as raffinate. That flows to a raffinate stripper. The objective of that raffinate stripper is just to remove the soluble amount of solvents from that raffinate stream. So it's stripped out and it leaves the raffinate column as overheads. Leaving the top of the extraction column, you have an extract stream that flows to a solvent recovery column. And the solvent recovery column, it's designed to yield both purified solute, generally speaking, off the bottom of the column, and also to recover the bulk of the solvent. So that solvent recovery column for this type of process is typically where the majority of the energy is used. So leaving the top of that column, you have an overhead stream, which has some water and mostly solvent. Those both typically flow into a combined decanter after the overhead streams are condensed. The aqueous liquid is refluxed back to the raffinate stripper. The decanted organic flows back to the extraction column as solvent, and the balance of that solvent flows back to the solvent recovery column as an organic reflux stream. So that's one way to approach a solvent extraction process where you have a high boiling solvent, and it's the typical method used in industry. If you have a non-volatile solvent or a low boiling solvent relative to water, the typical approach is using another extraction column downstream to recover the solvent. So here again, we have an extraction column. We have an aqueous feed stream coming in. It's contacted with an organic solvent. That extract or loaded organic stream leaves the extraction column. There it flows to something called a stripping column, which is typically contacted with pH adjusted water to recover the solvent and to remove the solid from the extract stream or that loaded organic stream, so it can go back to the first extraction column as regenerated solvent. And I'm going to be going through this in a little bit more detail in the second case study today. So pilot testing, of course, is critical for scale up. Whenever you have an extraction column, you always want to run a pilot test. And that's because there's complex phenomena that can take place right at the liquid-liquid interface, so that continuous phase and the dispersed phase within the column. There's a lot of things that happen there that are difficult to predict or anticipate ahead of time, such as if the system has a tendency to emulsify. That's something really difficult to predict in advance. What the impact of impurities or solids are on both operating the extraction column and if they have any impact on mass transfer or extraction efficiency. Coalescing of the droplets as they flow through the column on the column internals is also something that can have a huge impact on mass transfer. And also something we don't have a final determination of in advance is the stage efficiency within the column itself, how efficient the column is at doing that extraction process. So that's something we look to determine when we run a pilot test. So the best design method for a commercial extraction column in a solvent extraction process to treat a wastewater stream is to run a pilot test and then scale that up based upon observations made during the pilot test and established correlations and equations for the technology that was tested. So we have a pilot plant in Houston, Texas, that is essentially dedicated to solvent extraction pilot testing. We have the ability there to test with KARR columns with plate stacks as high as 20 feet and Schiebel columns with up to 150 agitated stages. Those are our two proprietary extraction column technologies, and I'm going to give everyone a quick overview on those two technologies in some coming slides before I get to the case studies. We also have the ability to test distillation and stripping columns for downstream solvent recovery or solid purification steps if needed. We also have the typical analytical capabilities in-house that you'd associate with a pilot facility, like GC, HPLC, and IC. And then if we can't do it in-house, we have really good relationships with other local analytical labs in Houston that can do the analysis for us. Back in 2018, Tom Lightfoot, who's our pilot plant manager, and myself wrote an article in CEP magazine on pilot plant testing for liquid-liquid extraction. Kind of gives our philosophy of designing and running a pilot test where we seek to optimize an extraction column in a very short amount of time and also minimize the amount of solvent and feed that are used to run a pilot test. So if there's interest, this is something we can share with anyone. There's a link that we can provide or a PDF of the article itself. So if you're interested, please let us know and we'll pass that along. So I mentioned the Schiebel column as one of our two proprietary extraction column technologies. The Schiebel column is a countercurrent agitated extraction column. The principle of operation here is there's a series of impellers that rotate within the column that create the dispersed phase and allow contact to take place between the continuous and dispersed phases. There's also a series of inner and outer baffles throughout the Schiebel column that prevent MAC mixing. So the combination of the series of baffles and the impellers within the Schiebel column that are rotating to create the dispersed phase, you have a really efficient extraction technology here. So if you have a process where several theoretical stages are required, the Schiebel column is going to be the right approach. Typically, when we compare different types of extraction column technologies to one another, we compare them in terms of their capacity. So that is essentially just the combined volumetric solvent and feed rates fed to the column divided by the cross-sectional area. The Schiebel column has very good turndown capability, 4-to-1, and that's essentially because you can control the speed of those rotating impellers within the column. It's not recommended for highly fouling systems or systems that have a tendency to emulsify. Highly fouling systems, there's a lot of area on those inner and outer baffles within the column, so solids or highly fouling systems can build up there. Also, if you have a system that has a tendency to emulsify, the high tip speed and the variable shear radially within the Schiebel column can prove to be a challenge for those types of systems. So we wouldn't recommend it for those applications. And then lastly, on the Schiebel column, its typical commercial operating speed is 15 to 75 RPM. So it's not a high speed device. And these next couple slides just show what the Schiebel internals look like. You can see in this first picture on the left, series of impellers and the inner baffles. This is for a 6.5-foot Schiebel column. The outer baffles are actually welded to the shell because this was a relatively large Schiebel column. And just for everyone's information, we've built Schiebel columns with diameters as great as 10 feet. And we're looking to go past that as well. Picture on the right just shows what an installation of a set of Schiebel internals look like. In these pictures here, again, you can see the impellers pretty clearly on the left picture, but you can also see the outer baffles here as well. That middle picture, you can see the inner baffles, but also the outer baffles, because the outer baffles are kind of identified by that outer Teflon ring, which facilitates their installation into a column shell. This is for a 30-inch diameter Schiebel column that we supplied a few years ago. Next, quickly, I want to talk about the KARR column. This is the other proprietary extraction column technology that we provide. The principle of operation here is a reciprocating plate stack. So there is a plate stack within the KARR column with a lot of open area, 55 to 60%, that moves up and down, and that's what creates the dispersion in the column and allows the contact between the two phases. The KARR column is extremely high capacity. It's the highest capacity of all the agitated extraction column technologies out there, between 750 and as high as 1,500 gallons per foot square per hour. It has good efficiency, the same turn down capability as a Schiebel column because you can control the speed of those reciprocating internals. One of the key things about the KARR column is it has uniform shear mixing. So nothing's rotating here. So the shear radially across the plate stack is the same. So if you have a system that has a tendency to emulsify, the KARR column is a great fit because you don't have that high tip speed at the edge of the impeller like a Schiebel column, and you have uniform shear. Also, if you have a system that has solids within it, the KARR column can be a great fit because essentially those suspended solids will just fall through the plate stack and go at the bottom of the column. Like the Schiebel column, the typical operating speed of a commercial column is 15 to 70 strokes per minute. So kind of a similar range there. And again, this is not a high-speed device. This is what the KARR internals look like. You can see in the middle picture, we have a series of plates, perforated plates, and you can also see there that the open area is very high, about 55 to 60%. And then on the right, we have a photo of some KARR internals being installed. That was a pretty tall plate stack height. I want to say between 50 and 60 feet. That's what the installation kind of looks like for a KARR column. These pictures show a very large diameter KARR column that we built a couple of years ago. One nice thing about the KARR column, and you can see this on the photo on the left, is that you can vary the plate stack height or the plate spacing throughout the plate stack. That's really an advantage of the KARR column. This is something we can do when we pilot test. If we see the system has a tendency to flood in a certain area, we can open up the plate spacing there just so less mixing is put in that section of the column so it can operate better. So now that I've kind of gone through the basics of extraction, a quick overview on extraction pilot testing and our technologies, I'm going to get to those case studies that I alluded earlier on the introductory slide of today's webinar. So the first case study we evaluated was a process where we had to extract phenol from a processed wastewater stream. Our customer referred to it as weak distillate. It contained phenol, methanol, and phenolic resin oligomers. The process specs were to generate an aqueous product stream that contained less than 50 parts per million phenol and also recover greater than 99.9% phenol. MIBK was selected as a solvent due to the published high distribution coefficient. If you look in DECIMA, you'll see 80 for the distribution coefficient using MIBK to extract phenol out of water. And this slide kind of shows what our pilot test setup looked like. Before we actually ran the pilot test, we worked with our customer to verify the distribution coefficient across a range of concentrations of phenol in that wastewater stream. We found it was actually had an average of 35, so less than the 80 that's published in DECIMA. And we think that's because of the presence of the phenolic oligomers that were in the wastewater phase, not as soluble in MIBK. So those are probably holding on to the phenol a bit, reducing the distribution coefficient accordingly. A Schiebel column was used to test this process. When we ran those equilibrium tests, we saw fast phase separation time, no tendency to emulsify. So that was going to be the right fit for this application. In advance, we determined that 6 theoretical stages were required at a reasonable solvent to feed ratio. The Schiebel Column itself had 60 stages, 3 inches in diameter, and all testing for this pilot test was conducted at ambient temperature. The key for the OPEX here and the CAPEX of the commercial process was really just to minimize the solvent to feed ratio. MIBK is a volatile solvent, so we're going to have distillation columns downstream. So by reducing the solvent to feed ratio, you reduce the overall energy costs and also the CAPEX cost a bit as well, as it reduces column diameters throughout the process. So whenever we run a pilot test, we run a series of runs to optimize the extraction step. And here we were just looking at that phenol extraction step, the single extraction column that's going to be in this process. So we looked to optimize the amount of agitated stages, the solvent to feed ratio, and we tested 2 different phenol feed streams. And all the tests we ran at a fixed scale-up capacity of 600 gallons per hour per foot squared. And ultimately what we found were runs 6 and 9, which are shaded in gray on this slide, were the optimal. We did run some tests at 42 agitated stages, but kind of looking at all the data, it was more appropriate to scale up based on 60. Makes the extraction column a bit more expensive, but it's a slightly more conservative design. And we found that the second feed was a little bit more challenging to process because although we were making our raffinate spec there, it had a little bit higher raffinate spec associated with it just because there's more phenol in the feed stream. So those are the 2 columns that we selected and the 2 runs that we selected to scale up. And this is what the overall commercial process looked like. So very similar to the slide I went through earlier, where you have a volatile solvent. So we have a raffinate stripper and a solvent recovery column. Coming off the bottom of that raffinate stripper is a stripped raffinate stream. So that's a stream that's going to have less than 50 parts per million phenol in it. And then coming off the bottom of the phenol recovery column, we're going to have a concentrated solute stream, which is phenol in this case, and it's a recovered phenol stream. But otherwise, it's very similar to that slide I went through before. And having that relatively low solvent to feed ratio for this process allowed for reduced OPEX and CAPEX in the commercial process design. So from that pilot run data, we were able to scale up to a commercial scale Schiebel column, which had 60 agitated stages. So whenever you test the Schiebel column, you use the same amount of agitated stages from the test in a successful run in the commercial design. So that's the same. That scale up capacity of 600 gallons per hour foot square per hour resulted in 16 inches in diameter. The solvent to feed ratio was 0.2, and the overall height was 30 feet. So this Schiebel column was designed and built and incorporated into a complete modular system, which also included the solvent recovery column and the stripping column and all the other things you'd associate with a complete process: instrumentation, piping, insulation, pumps, things like that, and a complete control system as well. And this system's been running successfully for a number of years now. Second case study I'm going to talk about today was where we were looking to extract a halogenated compound or a series of halogenated compounds from a wastewater stream. So we had a wastewater stream that contained 200 parts per million of non-volatile halogenated compounds. And a 2-step solvent extraction process was identified to reduce the halogenated compounds, leaving that first extraction column down to less than 50 parts per billion. So this is a classic solvent extraction process that has its roots in the mining industry. There it's referred to as hydrometallurgy solvent extraction. The extraction step used an extractant and a diluent. Here, the extractant was a tertiary amine, and the diluent was an aromatic organic compound or series of compounds. The tertiary amine is non-volatile, so distillation wouldn't be a viable option for solvent recovery. And as that loaded organic extract leaves the extraction column, then flows to a stripping column, like I showed on that slide earlier. And the pH adjusted water here is potassium hydroxide solution. So that's going to extract or strip those halogenated compounds out of the loaded organic or extract stream so it can be regenerated back to the first extraction column. And then leaving that stripping column, there we have an aqueous stream that's leaving, but it's heavily concentrated relative to the feed stream entering the process of inhalogenated compounds. So essentially what you have overall is that you're greatly reducing the volume of that aqueous waste stream that's going to be going off to downstream processing. So that's what makes this process so attractive. The pilot test setup for this had both a Schiebel and KARR column in them. So we were looking to test both extraction columns in this process. The Schiebel column was selected for the extraction step because of high density difference and fast phase separation time. And the KARR column was selected for the stripping step because their slow phase separation time was observed when equilibrium tests were performed. And we had experience with similar processes that had a tendency to emulsify. So right there, we knew that the KARR column was going to be a good fit here. The Schiebel column essentially was the same design as the previous case study, had 60 stages. Here we had C276 internals put in because there was a corrosion concern. And then in the KARR column, we had PTFE internals with a 12-foot plate stack height. Like the last test, all testing was conducted at ambient temperature. And really what we were looking at here was to reduce the solvent usage in both columns. The more we're able to do that, the smaller that aqueous stream leaving the stripping column was going to be, which would reduce the downstream processing costs immensely to treat that stream. So like the last case study, we're showing a series of runs on this slide. The first thing we did was optimize the extraction step. So we ran all these runs at a fixed capacity of 500 gallons per hour per foot squared for a scaled up column. We tested 2 feeds. So the first feed, we started off with that one. We were able to reduce the solvent to feed ratio down to 0.1 and completely blow away our aqueous raffinate spec, leaving the extraction column. And then in the next run, we switched to feed 2. This feed proved to be more challenging. We were still able to have a successful run with a solvent feed ratio of 0.1, but here the amount of aqueous raffinate, the amount of the halogenated compound in the aqueous raffinate stream increased substantially to 38 parts per billion, but this was still lower than our spec, so this was a successful run. So the next thing we did was we operated at those conditions in the third run in the first table to generate a high amount of extract or loaded organic so we could test the stripping step. And that's the run that you see in the second table. We used that extract or loaded organic from the extraction step to test out the stripping step. And although all the runs aren't shown here, we're able to reduce the potassium hydroxide solution solvent rate down to 0.2. So then we performed another production run with a stripping column to generate regenerated solvent so we can once again test the extraction step with regenerated solvent. And you can see in that last row shaded in a darker gray. In the first table, we were successful there as well. So we're able to completely test the process in our pilot plant. And although this process was never scaled up, both extraction columns could be scaled up, incorporated into a modular system, which would be provided with a process performance guarantee. The last case study I'm going to discuss today is one where we're looking to extract a quaternary ammonium compound from a brine feed stream. This feed stream contained 10,000 parts per million of that quaternary ammonium compound, which I'm just going to call a QUAT for short. The goal here was to produce a raffinate feed stream or raffinate product stream that contained less than 5 parts per million QUAT. The alcohol that was selected as a solvent immiscible with a feed was more volatile than water. So downstream solvent recovery steps would probably be distillation. Lab equilibrium tests that were done in advance yielded an average distribution coefficient of greater than 300. So because that's so high, not a lot of theoretical stages were going to be required here. We did a quick evaluation with the Kremser equation to determine a solvent to feed ratio of 0.1 would probably be substantial. And for the pilot tests, for this process, a Schiebel column was used. There's a high density difference between the feed and solvent, specific gravity difference of about 0.4. And there was a fast phase separation time associated with it when those equilibrium tests were run in the lab, less than a minute. So we knew the Schiebel column was going to be a good fit here. This column was designed with just 40 agitated stages. We didn't feel like we needed a lot here because we only thought 2 to 3 theoretical stages were required. It was also designed with an alternate feed point at 10 stages above the bottom. And that was done because we wanted to see if we could reduce the amount of agitated stages required for the scaled up column, if we could, to reduce the CapEx associated with the Schiebel column itself. So the keys for this pilot test were to minimize the solvent to feed ratio. And that was particularly because the downstream solvent recovery and purification unit operations weren't developed. So initially the extract stream will be sent to disposal. And because of that, we just wanted to reduce the amount of solvent and thus the extract stream as well as much as possible. In terms of CapEx, we were looking to reduce the number of agitated stages here and also the diameter as well by pushing the capacity during the pilot test, just to reduce the CapEx of the column itself. And again, here we have a series of runs. And the nice thing about this test is we can kind of show everyone how we optimize an extraction column. So first thing we were looking to do was to reduce the solvent to feed ratio. So initially we started up with a 40 agitated stages, a scale-up capacity of about 550 gallons per hour per foot squared, and a solvent to feed ratio of 0.1. There we were successful. We then tried reducing the solvent to feed ratio down to 0.6. 0.06, we were also successful there. We then tried pushing the capacity to 600 with synthetic feed. We were successful there as well. And then when we pushed it up to 650 gallons per hour per foot square, there we no longer made our raffinate spec. So we found the limit in terms of the operating capacity of the column. We then tried reducing the number of agitated stages down to 30 there to just save some CapEx on the commercial column. There we weren't successful. We no longer hit our raffinate spec. And at this point, we had just been using synthetic feed. So we switched from synthetic feed to real feed, and we ran at the same operating conditions that we did in run 11. There we were successful, even with a slightly lower solvent to feed ratio of 0.05. When we tried pushing the capacity again at the same conditions, otherwise, we no longer made the raffinate spec. So for scale up, we looked at run 23 and used those operating conditions. So if we were to scale this process up in a commercial scale Schiebel column, this is what it would look like. You have 40 agitated stages. That capacity of 550 gallons per foot square per hour translates to a 14-inch diameter. Solvent to feed ratio was 0.05. And the overall height of this column from the bottom tangent line to the top of the drive assembly, which essentially is the motor on the top, is about 25 feet. We also put 20-inch expanded ends on either end of the column, one for mechanical reasons to reduce the shaft length at the top, and also to minimize any potential entrainment of solvent in the bottom, because the continuous phase velocity here is pretty high because you have a low solvent to feed ratio. A complete solvent extraction system could be designed around this, so this hasn't been investigated yet. You would have a typical 3-column approach most likely here, with a stripping column to recover the alcohol from the raffinate, a distillation column to recover the bulk of the solvent, and possibly something like a thin film evaporator, white film evaporator downstream if you want to purify the QUAT leaving the process. So in conclusion, a solvent extraction process can be the most economical solution to remove wastewater contaminants because of the immense overall energy savings. You're not boiling off water, you're just recovering the solvent. So that's where those energy savings can come from. That selected solvent can be more volatile or less volatile than water, and that's going to impact the downstream solvent recovery operations. Like I went through in those initial slides in the case studies, if you have a more volatile solvent, typically you're going to have distillation downstream. And if you have a less volatile or non-volatile solvent, typically you're going to have one or possibly two extraction columns downstream. So when you're looking to develop this process, you can do some lab testing to determine the solvent, determine the distribution coefficients, and then really you should go into a pilot plant to test out all the extraction columns in the process, get some good data, scale up from that, and also incorporate that data into an overall process simulation. And then if you have a successful pilot test, we can provide a guaranteed process. And the other nice benefit about pilot testing is you're going to greatly de-risk the overall process as well. So that concludes the slide deck today. So I think we can open this up to any questions from the audience.
Yes, great. Thank you, Brendan. Appreciate you sharing that with us. We had a bunch of good questions come through. I'll start asking you some of these questions that came through. Again, if we don't get through all the questions, we will provide answers after the webinar, and then we'll also be sharing this content, the slide deck and the video, probably next week. We'll get that posted. So let me start with the first one here. First question is, can you run the countercurrent extraction column at higher temperatures to improve the distribution coefficient?
Yes, you can. What we find is that it doesn't typically improve the distribution coefficient, but it can have a huge impact on the extraction efficiency. So say you had a Schiebel column that was giving you about 4 theoretical stages with 60 agitated stages at ambient conditions. If you increase the temperature and the viscosity of both phases decreases, you can get greater mass transfer there. We often see this when we have a relatively viscous continuous phase. By increasing the temperature, you can reduce that viscosity and yield a much more efficient extraction process.
Okay, great, thank you. Another question is, can you define the term flooding inside the column? So for example, what is that physical phenomenon that's happening when flooding is occurring?
Sure. So flooding occurs essentially when you're pushing the column too hard in terms of flow rates or agitation speed. And essentially what you see is that the dispersed phase begins to build up within the column, and left unchecked, eventually you have both phases going out both ends of the column. This can happen if you have too much agitation speed. You're going to create finer and finer droplets, and with a constant continuous phase, you're going to have more drag kind of imparted on them as those droplets get smaller. Also, if you just increase the feed and solvent rates to the column, your continuous phase velocity within the column is going to increase. So that's another way flooding can occur. And when we run a pilot test in Houston, that's something we always look to do, is we always look to find the flood point, primarily because that's where an extraction column is going to approach its most efficient point, is as you approach that flood point.
Okay, thank you. Another question is, what do you recommend for recovery of the solvent which dissolved in the feed? So for example, in the MIBK solubility in water is 1.7. There's a lot to lose per batch.
So to recover the MIBK, it would be, typically speaking, a process kind of like this. I'll go back to the phenol extraction slide. Right, recovering the MIBK from the raffinate stream, leaving the column where you'd have that soluble amount of MIBK, you'd use a raffinate stripper there essentially. That allows you to recover the MIBK, and ultimately that recovered MIBK gets circulated either back to the extraction column or back to the phenol recovery column as reflux.
Okay, thank you. One other question is, in a typical system using a volatile solvent, what's a reasonable expectation for solvent recovery percentage?
I would say greater than 99% typically, because kind of going back to this earlier slide, for economical reasons, you want to recover as much solvent as possible, but usually there's going to be product specifications on the stripped raffinate stream leaving the process, and also the purified solute stream. Something we often see is an acetic acid process, and that will leave the bottom of the solvent recovery column, and typical solvents for that are ethyl acetate and MTBE. So you're not going to want to have too much of those in your purified solute stream. And if you have something like MTBE, you can only have ppm levels of that in your stripped raffinate stream as well. So for a process like that, you're going to be recovering 99.9% or higher of the solvent, and that's typically what we would strive for.
Great, thank you. Another one is, what are the materials of construction in the Houston pilot units? Can temperatures above ambient be tested?
That's a good question, and that's something I didn't get to. So you can kind of see it on this slide. The vast majority of the columns that we test, I want to say 99% of the time when we test an extraction column, it's going to have a glass shell, whether that's a KARR or a Schiebel column. Usually the internals for a Schiebel are stainless steel. For a KARR, they could be stainless steel or PTFE, depending upon which phase is selected as continuous and dispersed. But we also have a set of C276 internals for processes that are more corrosive. And we can also build pilot columns out of essentially any materials of construction that are required. C276, titanium, 2507, things like that, for the appropriate conditions or corrosivity requirements of the process. So there's a lot of flexibility there, but typically I want to say it's stainless steel. And if we need to upgrade that, we do have C276 internals that we can use.
Great, thank you.
But we can fabricate them out of pretty much anything, any standard metal alloys.
And then one last question that came in was, do you have good literature, reviews, papers on what type of solvent to use depending on contaminant types?
Yes, that's going to be from our experience, but we can also do literature searches as well, different solvent extraction handbooks and papers, and also using things like Decima as well. So that's something we very often work with customers on when we're developing a process, is identifying solvents, testing a series of solvents to identify the one that's most accurate or most effective, then doing more testing to kind of generate an equilibrium curve, defining those distribution coefficients across a range of solute concentrations. That's something you also always want to do. Then moving on to pilot testing and then scaling up from that.
So what would that look like? Would that be like a shake test, or what would that be?
Essentially, that would be a shake test to define the solvents first. A series of shake tests. And we use an apparatus that looks like, go back to the right case study, like this. So we contact solvents in feed in an apparatus like this. This shows a half moon impeller. This is what we typically use. Mix them together at high speed for 2 to 5 minutes, allow the phases to separate, take samples of each decanted phase, and analyze them to determine a distribution coefficient. So if you had a process you were developing and there are a few solvents that looked attractive, we'd run a series of these, say 1 to 2 shakes or mixed in decants per solvent and per feed, to identify the solvent that's most effective for that process.
I'm trying to recall, does the article that you and Don both authored, does it cover this as well?
There's a separate article that we have that covers it in detail. So it goes through our shake test philosophy, but also kind of gives background on liquid-liquid equilibrium data and how you can use it for developing extraction process. That was a Chemical Engineering Magazine article that we wrote 2018, 2019. So if anyone has interest there, they could reach out to us and we could provide a PDF or a link of that as well.
Great, thank you. That's all the questions that we had. I did want to just also mention that next week we'll have another webinar, which is on the topic of 3 differing approaches to industrial decarbonization. So we'll be looking at 3 different pathways and the, how modularization supported the project delivery of those projects. So please feel free to register for that webinar as well. And then there is a short survey at the end. Like once you leave this webinar, there'll be a short survey. So if you don't mind, just take 30 seconds, fill that out. That way we can fine tune future webinars. So again, I want to thank everybody for taking their time to attend this webinar and looking forward to seeing you next week. Thanks everyone. Take care.
Thanks everyone.
Bye-bye.